right, 10.1 looks at systems of equations, and actually the simple type. So you've seen these before. These are linear systems. In other words, here you see how the variables are power 1. Okay, so when I'm dealing with a linear system, I'm dealing with equations of lines. So what I have here is I have two lines, and the question is, can you solve the system? So when we say solve the system, what does that mean? That means we're looking for x, y pairs, and those have to satisfy both equations in the system. Okay, so if these x, y pairs satisfy both equations, then what I'm looking for graphically is I'm actually looking for intersection points of the two lines. In other words, I'm actually looking for points where the two lines cross. Points that they have in common. So in terms of actually solving the systems, well, I mean, we have some options. So I don't know. Let's look at this particular system. Say, okay, I mean, what is one thing I could do? I guess I could solve each equation for y. Let me look at that top one for a second. Divide by -6. Okay, let me look at the bottom one. Divide by 4. So there are my two equations. So I mean, one thing I was thinking was, well, I guess I could graph these equations, but I don't know how nice that's going to come out. Look, I'm just going to kind of do this roughly. I'd have to really be careful with my scale to do a nice graph with those fractions. So if I did this roughly, let's see, the top equation, let's see, I start at -1/3, that's the y-intercept. And then I go up 1 and right 2, it's going to look, I guess, roughly something like that. So that's a rough sketch of the first line. Let's see, the second line has a y-intercept of 1/4, somewhere around here-ish. And the slope, let's see, down 1, right, where am I? Looking at this line. So let's see, I had the y-intercept of 1/4, down 5, right 4. Okay, so I gotta go down 5. So 1, 2, 3, 4, 5, right 4. 1, 2, 3, 4. So it's somewhere right around there. So like I said, with these fractions in here, unless I really carefully scale everything, it's going to be kind of hard to tell what's going on. So if you look at this, let's see. I can't tell. I mean, what I can tell you is I have one intersection point. So this system of equations should have one solution. Okay, in other words, we call it a consistent system. It's a system that has one or has a solution. Okay, so the thing is, it's a little bit hard to tell with the graphing method. So the graphing method often falls short. Okay, that's where I graph the two lines and I look for an intersection point. So what's another idea? I mean, I can at least tell that I'm going to have a solution. So another thought is I could do a substitution. So look, what if I just solve the first equation for, say, y here? What if I take that then and I substitute that into the second equation? So now I'm doing a substitution. Let's see how that works out. So then I would have 5x plus 4. Then I replace the y with the half x minus a third. And that's equal to 1. Distribute the 4. Combine the like terms. Let's see, 3/3 plus 4/3, 7/3. One-third. Okay, so if I look at my graph here, I mean, I see that looks like it's at least in the right area. X equals a third. So what the heck is that corresponding y value? So I need to take that x value. I should be able to plug that into either equation, and I should get the same value since this is supposed to be a point that the two lines have in common. Okay, so then my point, my solution, should be the pair 1/3, -1/6. So I mean, looking at the graph, like I said, it's a little hard to tell where exactly does that point fall when you have those fractions in there. But it looks like that matches up. Now I can check. So let's see if I plug in the top equation. What is that? That's 1 plus 1 equals 2, yes. Second equation, 5 times a third plus 4 times -1/6. Let me see here. That's 5/3 minus 2/3. That's 3/3. Oh, look at that. Correct. Okay, so the method that I ended up using for that one was the substitution method. That worked out nicely. Here's another one. Okay, so typically I don't use the graphing method unless I'm really asked to. So I guess with this one, I could try the substitution method again. Let's see how that works out. So to use the substitution method, I have to solve one of the equations for one of the unknowns. So whatever looks kind of easy, like the top equation, looks like I can easily solve it for x. Okay, then I'm going to substitute that in to the second equation. Distribute. This one's interesting. Look at what I get here. -15 equals 2. But -15 does not equal 2. What I get here is a false statement, okay? A statement that's inconsistent. I would call this an inconsistent system. In other words, it actually has no solutions. Because, I don't know, do I want to graph this so I can see what's going on? Let's see. This guy looks like y equals x minus 5. And let's see, this one, let's look at this for a second. I have 3y equals 3x plus 2, divide by 3, so this one would be y equals x plus 2/3. So there's what my system of equations looks like if I solve for y. So you can see immediately what's going to happen here, even if I don't do a fancy graph. But I'll do a rough sketch. But there's something important that I notice about the slopes and the y-intercepts of those lines right away. you see how y equals x minus 5. 1, 2, 3, 4, 5. Here's the y-intercept. Slope's 1. Rough sketch, okay? The second line, the y-intercept is 2/3, but the slope is still 1. Okay, so the line, look at what's going to happen. It's going to actually be parallel to the first line. Okay. So I notice the two lines are parallel. That means they go on forever but never cross because they have the same slope but different y-intercept. So as soon as I know that, I can tell you that system is going to be inconsistent. In other words, it's going to have no solutions. Those lines are never going to cross. What's the other method I could have used? There's another method we use that's called the elimination or the addition method. So if you look at that original system, what the goal is with the elimination method is to add the equations together and eliminate or cancel a variable. If I were to just add the two equations together as they are, it wouldn't work because here's what I would get. So nothing was eliminated. So most of the time, if I'm going to use the elimination method, I actually have to first manipulate the system, as in like multiply one or both of the equations by something so that I end up getting the same coefficient on a variable but with the opposite sign. As in like, see how, what if I multiply this whole top equation by a 3? You see what's going to happen? Look, I'm going to get, so let's do that first. I'm going to get 3x minus 3y equals 15. The bottom equation, I'm going to leave it as it is. But you see how now if I add on both sides of the equal sign, I'm actually going to be able to cancel out the x's, but actually also the y's. So you see how even when I use the elimination method, I still end up getting a false statement. So again, I would still conclude there are no solutions. This is an inconsistent system. So lots of options. Here's another one. I don't know, that one I kind of notice when I'm looking at it that I have similar like coefficients. Like you see what I mean? If I were to multiply this top equation by like -3, the coefficients are going to line up here somehow. So that kind of leads me to think, I mean, I might try the elimination method for this one. That seems easy. So what if I multiply that top equation by -3? -9x plus 3y is -21. Second equation, I'm going to copy it down as it is. So what happens here? So is this the same as the last one? Well, be careful. Cancel, 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 but the right side also cancels. So actually this time I don't get a false statement. I actually get a statement here that's always true. 0 is always equal to 0. So this statement is always true, no matter what x is. So what is this saying? This is saying that the system has infinitely many solutions. So how could we, let's look at this graphically for a second. So let me solve the equations here for y. So let's see, this one would be y equals 3x minus 7. Let's see, let me look at this for a second down here. So 3x, oh, look at that. You see how I actually have two equations here? But really I don't. I really have the same line written twice. So I have the same equation but written in a different way. So if you think about what's actually happening graphically here, you really only have one line. So look. I'll do a rough sketch. Let's see, the y-intercept's negative 7. 1, 2, 3, 4, 5, 6, 7 is here. Slope is 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So that's a decent sketch, actually. All right, but then I have that line, and then the same line comes along and goes right on top of the first line. So then the question is, what are the intersection points of these two lines? But actually, if you look at what's going on graphically, all points on the line are intersection points. In other words, so the system has infinitely many solutions, yes, but where are all of those solutions? Well, all of those solutions are points on the line. Okay, so how would we write this? So we would say something like, we say this is we call this one a dependent system. So dependent system, and then we'd say there are infinite solutions all on the line y equals 3x minus 7, where x is any real number. So this is how I would write the answer. I would write all of that, really, because here's what we're saying. We're saying you can pick any value of x, plug it into this equation, get the matching value of y. In other words, the y that you get out depends on the x that you plugged in. That's why it's called a dependent system. And then this system has infinite solutions so long as we're on the line. So like, I mean, that's really all I would write. But if you wanted to like see how this actually works, like, what if you pick a value of x? I don't know, 1. Plug it in here. Y equals 3 times 1 minus 7, so negative 4. So supposedly, the point 1, negative 4 is on that line. So 1, 2, oh, look at that. There's that point. So it works, right? If I plug in 0, I'm going to get negative 7. Okay, so I'm going to get all the solutions, all of the points that lie on this line. So that was just to show how that works. That's all you need to write in terms of the solution. Here's a word problem. Juan invests a total of $5,800, some in stocks and some in bonds. The stocks pay 3% interest, the bonds 4%. The end of the year, he's earned $213.50 in interest. How much did he invest in stocks and how much in bonds? So we're going to assume that this is simple interest. Be the implied assumption here, and then let's see. We're going to assume that these are annual interest rates. Say that's another implied assumption. So let's see what we're dealing with. So, what are our variables? What are our unknowns? How much did he invest in stocks? So I don't know, should we use S? The amount Juan invests in stocks. How much did he invest in bonds? Okay, then what do we know? So Juan invests a total of $5,800. In other words, if I take the S and add it with the B, I should get a total of $5,800. The stocks pay 3% interest. So for whatever amount he invests in stocks, he's going to earn 3% of that. Then he's going to add in the amount he earns on the bonds. He earns 4% of whatever amount he invests there, to give him a total of $213.5 in interest. So I kind of have two equations. This one represents the total money. This one represents the interest. Okay, so now I need to solve this little system. So I think what I would do is I'd probably take the second equation. I don't like those decimals in there. If I multiply the whole equation by 100, when I do that, I move those decimals 2 places to the right. So what the heck do I end up with there? Let me bring the top equation down for the moment. So I'm going to have 3s plus 4b, that's a lot nicer, 213, and then 50, 21,350. And now I decide how I want to do this problem. So I don't know, I could really do substitution or elimination here. I guess looks like a pretty simple substitution problem, either way. So I'm going to have 3 times 5,800 minus b plus 4b equals 21350. So I replaced the s here with the s here. Now I'll distribute. So that's 174, add 2 zeros. 3 times 6,000 would be almost 18,000. That seems good. Okay. Combine. Oh, that comes out nice. Just B. So then we just need to subtract. $39.50. Okay, and then don't forget I have to also get the corresponding value for the S, the stocks. $18.50? Did I get that right? So you can just check the arithmetic, make sure those add up to the right thing. 3, 4, 5. Double check. 0, 0, add a 1, 10, 18, 3, 4, 5. 5,800 was the original amount. All right, so then what the heck is the answer to the question? Because I can write something. Let's see, Juan invests, what was that one? $39.50 in bonds and $18.50 in stocks. That wasn't too bad. Couple more. A candy shop sells chocolates for $6.50 a pound and nuts for $4 a pound. The shop wants 200 pounds of a mixture of the two that will sell for $6 a pound. How many pounds of each should be used? So there's no change in revenue selling the mixture versus individually. So first thing I see is how many pounds of each. So I guess I'm going to pick my variables. So C, let's do the pounds of chocolate. And then N, the pounds of nuts. Okay. So what else? How can I start my equations? Let me see. The shop wants 200 pounds of a mixture. So I guess if I add my chocolate with my nuts, the pounds of each, I should end up with 200 pounds. So this is like a total pounds equation. Okay, what else does it say? The candy shop sells the chocolates for $6.50 a pound and the nuts for $4 a pound. So let's see, if I take $6.50 and multiply it by the pounds of chocolate, $4 and multiply it by the pounds of nuts, that's going to add up to the total revenue. Like, let me say it this way. This would be the revenue from selling the nuts and chocolates separately. Did I get that right? I think that's actually an E. No, I got that right. Okay. Anyway, so then what is the revenue from selling the mixture? Candy shop sells the chocolates for $6.50 a pound, the nuts for $4 a pound. The shop wants 200 pounds of a mixture of the two that will sell for $6 a pound. Okay, so the mixture let's see. That's going to sell for $6 a pound. But how much is there going to be? There's going to be 200 pounds of that mixture. So those are my two equations. That bottom equation, again, it says $6.50 a pound for the chocolates, $4 a pound for the nuts. That'd be the revenue if I was going to sell those two things individually. From the mixture, it's $6 a pound for 200 pounds of that mixture. That's that revenue I'm going to generate from selling the mixture. And so it says that there's no change in revenue selling the mixture versus selling the two individually. So I know those two things have to be equal. Okay, so there's my system. So for this one, it's a little more interesting to set that system up. So let's see, I have that equation. Let's just start by, should I multiply, what is that, 1200? And then I don't know, how do I want to solve? Should I do elimination for this one? That might be fun. I could multiply this whole equation by -4. Therefore, let's see, it have -4c minus 4n is -800. Add together on both sides of the equal sign. So what is that? 2.5c is 400. So I got a couple options what to do from there. I guess I could multiply by 10. And then divide by 25. Okay, let me see here. What is 400 divided by 25? Let me see. 100 divided by 25 is 4, right? So 400 divided by 25 would be 16, and then add a 0. Did I get that right? 160. Okay, now I still have to get the matching n. So let's see. C plus n is 200. So n would have to be 40. So what is my conclusion? 160 pounds of chocolate, 40 pounds of nuts. A theater charges $9 for adults and $6 for kids. On a day when 250 people attended, total revenue was 2232. How many adults, how many kids attended? So let's see our variables. All right, a theater charges, let's see, let me start with this actually. 250 people attended. So if I add the number of kids with the number of adults, I should end up with 250. This is the total people equation. The other equation will be for the revenue. So it's $6 for kids, $9 for adults, and that should add up to the 2,232. Okay. And then again, I have some options. I don't know. I guess I can solve that first equation for K or A, really. I don't know which one would be easier. 250 minus A. Substitute. Six times 250 minus A plus 9A is 2232. Let's see, 2 times 250 is 500, so times 3, 1500, is that right? Divide by 3. $244. So 244 adults. And let's see. How many kids then? Oh, not very many. This must be a scary movie. 6 kids. And that's it.